Understanding electric fields, and more specifically this term called voltage, is probably one of the most abstract and hardest things to understand we're going to look at all year. So I'm going to try and walk you through what each one is individually and then try and show you how they're connected. So the first thing to understand is if I took a ball and I dropped it, obviously the earth would pull that down. It's the force of gravity. And if I had a negative and a positive charge and placed them near one another and let go, they would attract one another because opposites attract. But the thing we haven't really discussed, but you may have noticed, is in these two cases, there's absolutely no contact required. The earth can pull on that ball across space, and these two charges will be attracted to one another regardless of whether they are physically making contact. And that's because these forces, gravity and the electric force, are what we call field forces. So there is what we call a field permeating through space, and that's what allows gravity to pull on an object across space and allows two charges to attract or repel one another. So it's just important to understand that a field force is a force that can be exerted through space without the need for physical contact. So the contact forces are the ones that we've discussed so far: friction, normal force, applied force, tension. The field forces, gravity we've discussed, the electric force we're currently going to begin to look at. There's also the magnetic force. If you've ever played with magnets, you'll notice they're able to affect one another without having to physically touch. So just to begin, just try and understand the idea that there are certain forces in the universe that don't need physical contact in order to exert themselves. In order to understand these fields, we need to understand how to draw them. And again, just drawing them is a good visual way to kind of see what's going on. And drawing fields is actually fairly straightforward. So with a gravitational field, if you want to test a gravitational field, let's say in the classroom, you'll just hold a mass at different locations. And obviously, if I let go of the mass at any given point in the classroom, whether it's near the floor or near the ceiling, it's going to act down. The force of gravity acts downward. So if we kind of look at this and we notice that wherever I hold this mass, it's pulling down. Well, if we want to draw the gravitational field, well, we use what are called field lines, and they just represent the force. So since the force of gravity is always acting down in the classroom, it's just a bunch of lines that are all pointing down. Because anywhere I hold a mass in this classroom, these lines show me that it will be pushed downward or pulled downward by the force of gravity. The only thing to make note of now, and we'll get into it in a little more detail later, is the spacing of the lines is important as well, because it tells you how strong that force is. So in the classroom, we don't necessarily feel heavier or lighter if we're on the floor or near the ceiling. We generally feel the same weight. So the reason why these are all roughly evenly spaced is to show that in the classroom, no matter where I hold a mass, it's going to have the same weight. Okay, the spacing of these lines is not going to change unless you start to get really far from the Earth, because obviously gravity has less of an effect, so that spacing will get wider. So the closer together these lines are, the stronger the force. The further apart they're spaced, the weaker the force. But the basic idea to understand now is that because these masses are all being pulled down, that's why the gravitational field is just pointing downward. Now, I'm going to make a lot of analogies to the gravitational field to help explain the electric field. So in this case, instead of the Earth or a classroom, we have two plates. One of them is positively charged and one of them is negatively charged. Now, anytime we want to test a field, just based on convention, we use what is called a positive test charge. We have two types of charge, positive and negative. Just to make sure we are all on the same page when talking about these electric fields, we always assume the test charge that we're using is positive. So just like you test a gravitational field with a mass, we test an electric field with a positive charge. So similar to this gravitational field, whenever I place a positive test charge within this field, it will be repelled downward by the top plate, but attracted downward by the bottom plate. So no matter where I place this charge will be forced downward. So if you think back to our kind of field line rules, if the force on this positive charge is pointing downward in all of these cases, then my electric field quite simply is a bunch of downward pointing lines. And because this is a parallel plate arrangement, we get a uniform field. So all that means is the spacing between these lines is going to be even. Because just like in this classroom, it doesn't matter where you go in this classroom, you'll weigh the same. Between two parallel plates, wherever you go, you will experience the same force. So hopefully at this point you understand the basic idea behind drawing these fields. And the fact that a field force is a force that can act over space. If you do, it's time to talk about voltage, which is probably the hardest thing to understand of anything we'll look at all year. So I'm going to do my best to try and give you some good analogies, some good examples to try and reinforce what voltage actually is. Because we've all heard voltage, 9-volt battery, 3-volt battery, but I don't think too many people actually know what it actually means. So again, let me start by going back to an example we've looked at in the past. So if we're in this classroom, we'll assume it's on Earth. I'm going to round the 9.8 to 10, just so it's a little bit easier to do this without a calculator. And if I hold a 1, a 2, and a 3 kilogram mass 1 meter above the ground, I can calculate the potential energy that these three masses have, because it's just m times g times h. So for the 1 kilogram, my mass is 1, my gravitational acceleration g is 10, and it's 1 meter above the ground, so that object will have 10 joules. The 2 and the 3 will have 20 and 30 joules, respectively. So that's something we've discussed. What we haven't discussed, and it's not really something we're going to use, there is another term instead of gravitational potential energy. There's something just called potential. It's not potential energy, just potential. And all it is the rate at which that energy is being gained. So yes, the 1 kilogram mass has 10 joules physically at that location. The 2 and the 3 have 20 and 30. But if we look at the rate at which they gain that, or the amount of energy they get per kilogram, you'll notice that I get 10 joules when I place 1 kilogram there. So that gives me 10 joules per kilogram. The 20 joules is possessed by 2 kilograms at that same location. So the 20 joules it possesses divided by the 2 kilograms of mass gives me 10 joules per kilogram again. And similarly with the third point, the 30 joules split among the 3 kilograms. I forgot to write this in, but that should be 10 joules per kilogram. So what we're recognizing is while the actual amount of energy these objects possess is different, at a 1 meter height, anything placed along this line will get 10 joules per kilogram. So now I'm able to say if I hold a 5 kilogram object at this dotted line, well, I'm still going to get 10 joules per kilogram, but if I bring 5 kilograms, I'll have 50 joules. If I bring 10 kilograms, I'll have 100 joules. So it's a very kind of minute distinction, but the energy is what the mass physically possesses. What we call the potential is the rate at which it gains that energy, or how much energy it gains per kilogram that it has. Okay, so if that kind of makes sense, let's try and see how this applies to an electric field. I'm not overly concerned with the math, but I do want to explain really quickly where I'm getting these values from. For gravitational potential energy, it's your mass times your gravitational field times your height. We can just substitute out the values. If I want to know the electric potential energy, we're not dealing with masses in an electric field, we're dealing with charges, and Q just means charge. So Q in this case would be like my 1 coulomb, my 2 coulomb, or my 3 coulomb. We're not dealing with a gravitational field, we're dealing with an electric field. So in this case, I'm still going to use my value of 10, but you get 10 newtons for every coulomb you bring. So this is basically like the electrical equivalent of 9.81. And instead of height, we're going to say distance because it's the distance you are from a given plate. So again, you don't have to go crazy trying to fully understand this, but we're just using MGH, but we're replacing it. Instead of mass times gravitational field times height, it's charge times electrical field times the distance above your negative plate. But it's essentially the same equation. Only reason I went over this is so that if I want to calculate the electric potential energy, you understand what I'm doing here. I'm taking the 1 coulomb charge, I'm multiplying it by the strength of the electric field, and it is 1 meter from the negative plate. That will give me 10 joules of potential energy. In this case, it's electric potential energy. For the 2 and the 3, similarly, it's going to give me 20 and 30 joules. But more importantly, while those are the specific energies these charges possess at this point, the voltage at this dotted line, if I remove those charges, anything placed on this dotted line will get 10 joules per coulomb that I bring, and what we call that is a volt. So a joule per coulomb is a volt. So we say this dotted line, because when I divide by the amount of charge, it gives me the same value. We say there is 10 volts, or the voltage at this point is 10 volts. Any charge I place there will get, 10 volts means 10 joules per coulomb. So if I bring 1, I'll get 10. If I bring 2 coulombs, I'll get 20. If I bring 5 coulombs, I'll get 50. So the voltage is not a property of the charge. A voltage is the property of a location or a region in the field. So the potential energy is something the charge possesses, and the voltage is something the field possesses. This is kind of very hard to understand. I will go over this and give you plenty of opportunities to try and fully understand this. But one of the analogies that I like would be like if you had a job. You work 5 hours, and your hourly rate is $10 per hour, so you bring home physically $50. Well, in this case, the amount of hours you work is analogous to the amount of charge that you bring. The hourly rate is synonymous to the voltage, or the rate at which you gain that energy, and the physical money you bring home is the physical, or analogous to the physical energy the charge possesses. You could work for 10 hours, 15 hours, or 100 hours, and that will certainly change your total. However, this will never change. Every time you work for another hour, you use this rate to figure out how much money you physically possess. This will not change. But more coulombs times the same rate will give me more energy. So property of the field, property of the charge, property of the charge. And the very last thing we need to understand is a more conceptual understanding of how do I know if the voltage is increasing or decreasing, as well as the energy. So again, I'm going to go back to gravity. Let's assume we have a mass that I'm holding some distance above the ground. If I move it upwards, if I move it opposite in the direction where it wants to be, which is on the ground, if I move in the opposite direction, it's gaining height, so it now has more potential energy. So when I force this mass to do the opposite of what it wants to do, it will gain energy. Conversely, when I move it downward and I move it in the direction that it wants to go in, it loses energy. And that's kind of what we just have to understand here. When a mass or a charge is doing what it wants to do, it's going to a lower energy state and it loses energy. But if I force it to do the opposite, it's gaining energy because I'm making it do the opposite of what it naturally wants to do. So how do we apply this to electric potential energy? Well, we can do the same thing. If I have a positive charge and I hold it in the middle of these plates, well, if I move it upwards, that is the opposite of what it wants to do. A positive does not want to be near a positive plate, and it does not want to be far from a negative. So forcing it to do the opposite of what it wants to do, it gains energy. Forcing it to do what it wants to do will cause it to lose energy. So when a charge is moved in the direction it wants to, I use quotes because obviously it doesn't want to do anything, but when I move it in the direction it wants to go in, it loses energy. When a charge is moved in the direction it does not want to go in, as in over here, it will gain energy because you're forcing it to a region where it doesn't want to be, and you get a much stronger repulsion from this positive plate. In terms of voltage, it's the same basic idea, but remember, voltage is a property of the field or a region. Electric potential energy is what the charge possesses. So when I want to look at voltage, there are no charges. There's just regions of space, there's just points. So this is a region where a positive charge would not want to be. If I place a positive charge anywhere in this region, it does not want to be there. So we say that is a high voltage, because if I placed it there, it would have a lot of energy because it doesn't want to be there. So the voltage has to do with how much energy that region will give the charge. So a region where a positive does not want to be is a high voltage region, and a region where the charge or the positive charge would not mind being, where it kind of naturally wants to be, we say that's a low voltage region. So if I just took 3 different readings throughout this field, I would get a reading of about 50, 20, and 10. As I'm moving from a region that a positive charge does not want to be in towards a region that a positive charge likes to be in, well, as I do that, I'm going to drop in voltage for the same reason that as that charge is physically moved, it loses energy. That means that this is a low energy region and a high energy region. We just have to understand electric potential energy, you're talking about the charge and what the charge possesses. And voltage, you're discussing the region of the field and what that region will provide a charge when it shows up. Again, very confusing topic. Do the best you can to just at least initially internalize this, and we'll make sure that over time you more fully understand exactly what's going on here.